All right. So it's my pleasure to introduce our next speaker, Dr. Loren Alegria. He got his PhD with Professor Jason Petta, working on spin qubits over at Princeton University. And after that, he's now at Livermore National Laboratory, where he works a lot on the fabrication and design of superconducting qubit devices, and I also have the pleasure of working with him on a few projects. And so I know he's going to give a great talk. And so everyone, please give a round of applause for Dr. Loren.
So yeah, thanks to the organizers for this crazy, amazing event, uniting all different disciplines and a lot of the the stars of the qubit design world. My contribution is a bit more on the material science side, and I'm hoping to provide some perspective on how materials kind of intrude into the design problem for superconducting qubits. And my title about ontologies for language model era, whatever that means, is just that, the design problem is kind of, as we've heard, spans many length scales, disciplines, software packages, and, specialties in physics. And in my perspective, the large language models are especially capable at uniting terminology and, for instance, arriving at sign conventions and things like this. You can imagine doing that sort of thing much more efficiently. So my hope is that in this brave new world of AI, we can really accelerate and integrate the development of software for superconducting circuit design. So I will be talking about our qubit fabrication process that we have at Livermore, and walking through it, while also describing some of the kind of up and coming questions in the material science for superconducting computing. And the kind of big figures of merit are how well defined the junctions are, how much loss there is in the junctions, and similarly how much loss there are in ground plane structures, and how well defined those are. And from a material science perspective, that's a lot of what we think about. So the part of a superconducting qubit is a Josephson junction, and throughout this workshop, it's been abstracted as just a rectangle, of course. It's very useful to have these abstractions for circuit design, but we know that the reality is far more complex. And so from my perspective, what a superconducting qubit is, looks a little bit more like this. Hopefully you guys can see this pretty clearly, but a superconducting qubit is essentially just an SIS structure. And your insulator is both the substrate and a thin oxide layer separating in most cases aluminum electrodes. So this is a junction from a recent device, and you can see that there's all kinds of structure not captured by our models of microwave design, which we would like to be. So for the purpose of like bandgap engineering, it's quite common to have a very thin lower electrode layer of your aluminum. Some nice work from Google recently about that. And then a much thicker top electrode. And you can see, by eye, that these are very different kind of systems. The the thin layer versus this very grainy top aluminum layer. They have complex characters imparted by the deposition process. So there's the top layer has this columnar structure that comes from the angled deposition. And you can see, especially in devices made on sapphire like this one, every last particle, that there's kind of a boundary regions along edges that likely contribute to junction loss. And as a field, we would really like to understand better exactly how every interface works, and in the interest of actually advancing the fundamental elements of superconducting qubits, we'd like to have design models that actually tell us some information about what we can do to make these better. And part of that is having complete models to kind of reference to experiments. So I mean that's mostly to say that we, in this picture, we want to go to finer length scales to understand the loss throughout the device. Going to even finer scales with simulation is getting into other disciplines that aren't that's a whole other thing. But this is a TEM just to give you some sense of what almost all Josephson junctions in conventional superconducting qubits, made by pretty much all the major research groups. What it looks like at a kind of atomic scale. So this is the sapphire substrate. This is the bottom aluminum electrode. Then that's the junction, about 2 nanometers thick. And then this is the top aluminum. And you can see like a grain boundary that's moving through the lower aluminum layer, and it's introducing some cusp into the Josephson junction. And this is essentially the origin of the uncertainty in the Josephson energy that tends to randomize qubits. So ideally, we would, we'd like to get beyond the shadow evaporation process, and there's many efforts underway to do that. Essentially, you'd want to go to something like a tri-layer process where you're making an extremely uniform multi-layer structure and then fabricating that into a qubit. Nonetheless, that introduces a variety of more, many more interfaces, and for that we in particular need improved models of loss. But for the moment, the shadow evaporation process is extremely successful, and so we shouldn't take it for granted.
Can you pause a little, like a minute for questions about the images you just showed?
Sure, yeah, any questions at any time.
So there's one question in the Q&A. In the SEM, which is the oxide layer in the SIS structure? Maybe you can point that out.
You can't see it. Wait. So in the SEM, you can see maybe 5 nanometer length scale, best case scenario. The junctions are about 2 nanometers thickness. If you section your device and have the best SEM, perhaps you can see the junction. Yeah. But if you just put your device in the SEM, you will not.
What we are on SEM subject. So you said that the bottom layer aluminum is epi, and then the top layer aluminum is deposition.
No, in this case.
No. Because they look similar and.
Yeah, exactly. So no, but with any material system, as you grow thicker films, you develop grain structure. So in the thinnest films, you don't see grain structure. You don't see a visible grain structure. That's why it looks smooth. It's not. It's the same. It's the same deposition process. It's just thinner. That's okay. Yeah. So let's not take shadow evaporation for granted. It's served us well for the past 40 years, right? It's been kind of the foundation of our understanding of mesoscopic superconductivity. And in recent years, people have developed all kinds of new tricks for making junctions in cleaner ways that, ways that don't have parasitic junctions. So those are regions that aren't the junction, but still have overlapping aluminum layers. That's what this figure is showing. And yeah, I would just argue that we haven't seen the end of shadow evaporation. There's many games to play, and if you look at the literature, there are as many approaches to making a junction as elements in the periodic table that just using shadow evaporation. So this is a selection of junction geometries that we've experimented with at the lab. And in each of these, you have a suspended shadow mask. This is usually photoresist. It can be inorganic, and like Lincoln Labs has developed an inorganic shadow mask process. And various combinations of angles in order to build up the structure. So like in the first example here, which is quite conventional, you just kind of deposit aluminum down one of these channels and then tilt the substrate. I hope it's roughly clear, but this is in each of these cases, the arrows are showing kind of deposition at a tilted angle relative to the substrate to form these shadow structures. So there's lots of room for innovation in this. And one reason that there hasn't been is, practically speaking, is that if you do this in your lab, your grad student, and you figure out all the geometry, all the trigonometry to find your angles, and like figure out how to carefully align your chip after you do your development, you're pretty tied to that procedure, right? So most labs, once they develop a shadow evaporation process, they kind of just stick with it. So it'd be great if there were design tools that enabled us to do this more flexibly and just kind of automatically develop kind of these shadow evaporation processes. And so I wanted to use this as an example for what I was talking about using large language models to improve our design tools. So I have previously, for my own purpose, written like Python scripts for calculating shadow evaporation processes, but I wanted to just demonstrate how one can use a particular like agentic AI coding for developing a very similar geometric calculation. And so I'm curious, like, if people have used either Windsurf or Cursor. Has anyone in the haven't used? Okay, you have to. It's crazy. It's totally crazy. So these are Windsurf or Cursor are they're IDEs, so they're GUIs, kind of like VS Code. They're forked from VS Code, but they use a large language model agentically to develop code, and they use as context. So when you use a large language model, you're giving it some context. So that's your prompt and the words and the history of your conversation. So they use as context your code base and a conversation. So this is like what the GUI looks like. It's like writing code normally, but so the left has your file structure, your code base. You have an editor, and then you just have a kind of chat panel where you interface to a large language model, and it will both write code. It will tell you about the code. It is a verbal interface like you might anticipate.
So is it something similar to Copilot and VS Code?
It's
more advanced version.
I think it's more advanced. It's like Copilot, you know, it does the same things, but I think I mean, I think you should try and see if you think it's better, but I think it's considerably, it does more. Yeah, I mean, so I don't want to be like an expert in this. I don't really think there are a lot of experts in this at the moment, but I just wanted to demonstrate, you know, capabilities. So this is using Claude 3.7. So this is a language model from Anthropic, and you know, you can use any of the most advanced large language models through this. It takes a context that you define, and then it sends it to either OpenAI or Google or whatever to do the query. And so here I just wanted to demonstrate development for this little shadow evaporation designer. So this is my prompt that I'm putting in. And so, yeah, as I say, I've done this before, so I have some idea what it is that I want. So I say propose an approach to making a complete website deployment. The functionality would be to upload a GDS file, etc., and make a GUI to display this and allow the user to download this. And then I spell out in excruciating detail the geometric operation, you know, just like you did handwritten proofs in geometry, or at least, you know, at some point, so that there's a complete logical picture of what the software does. And the first two steps of this are just, it's not asking the system to write any code, it's just to formulate a plan. And then these two prompts are just to tell it to do the code. So that after these, it came up with a plan, and then it came up with seven steps. These are steps involving creating, you know, files, downloading packages, and so forth. So in like the course of a very short time, with just those prompts, it generates this user interface, and it's you know, it made this thing website where you can upload a file as promised. You can define different angles, and then download the result that calculates this pretty simple geometric projection operation, but something that, you know, took considerably longer to write, maybe order of magnitude or two longer to write that when I wrote it myself. So in my view, crazy powerful. Okay, so this is just to show that it works. This is an input GDS file, and then the yellow perimeter is the result of development. So when you do electron lithography, you develop an undercut that allows you to make this ridge structure and shadow evaporation. And then you get the result of the calculation is kind of stupid, perhaps you might think, but it's just to project and kind of perform some Boolean operations to predict what the result of depositing at different angles. So you get this, but it just kind of works. So yeah, I would really encourage you to try, especially if you're daunted by given by how many packages there are for integrating within the circuit design problem. These systems are very useful at learning about how code works, learning about how your own code works, like reminding you. They're good for porting to new systems. So if you need to convert a bunch of code for a new package, for example, and good at generating documentation. So not only do they kind of turn pseudocode into actual code, they go the other way and can allow you to extract the logic in an accessible way. So they have shortcomings, of course. You guys are probably familiar, but they avoid runtime errors at almost any cost. So there's a few things, but I would just strongly encourage you all to try for yourself. And it's kind of a weird art that no one knows how to do well, but it does work in my experience. All right, that's enough of me raving about AI. So back to the qubit fabrication world. So you have to do deposition of aluminum at different angles, and a kind of more mundane but quite important process is that you have to form good electrical contact between the Josephson junction and the superconductor that forms the rest of the circuit. So there are kind of three approaches to this. You can either put one big swatch of aluminum over your contact in a second lithography step. You can do what is shown here, which is an in situ bandaging approach where you do you have like a third angle, a third deposition angle, and do an etch and aluminum deposition. So these are all examples of doing that. Or you can do a third thing that I'll show, which is just to do an etch at a third angle again, and initially, and then the deposit. So the consequence of that is shown in the lower panel here, using this little shadow calculator that we just made. So if I perform the etch at 2 incident angles, you etch these large contact regions without damaging the region of your mask where the junction lives. And if you make the junction leads too wide, you end up etching in those regions. So this is people are quite fussy about making sure not to damage, for instance, the silicon beneath the junction. So we're gonna, yeah.
Angle etch,
Which?
like with respect to like direct etch, is it in this case it's milling, like argon milling,
Yes.
or whatever. So what is this angle versus direct angle?
So so this is so if this is your shadow mask that you're looking down at, it's a directional etch, as you say, into the plane, but at an angle like this. Does that make sense?
I mean, why
Yeah.
it is angle? Why it's not just not angle?
Why you mean why
Is
why
that-
not just etch like at normal incidence? The reason is that when you do this etch, it's bombarding it with high energy argon. So you will amorphize silicon. You'll kind of make a cratered silicon surface and so then you're going to put your junction on that, and that can lead to loss in the junction. That's the so you use the angle to avoid etching in the region where the junction will live by one of these methods. So when you make junctions, they're kind of all over the place. You have random, you kind of have a random distribution, as I mentioned, of junction resistance. And to me, this is kind of one of the fundamental problems with our current superconducting circuits, if you think about what a qubit is, it's a very high quality resonator, right? So if you have a 500 microsecond T1 time, you have a line width that's like 2 kilohertz or something. It's very well defined object in frequency space. But now, you know, the result of fabrication is only accurate to within 100 megahertz. So there's orders of magnitude between what a theorist anticipates a qubit being and what comes out of fabrication, right? And so, in a sense, I think there's an opportunity. You know, if you imagine this, like we're all kind of playing piano, it's like we could fit, you know, 5 orders of magnitude more keys between each key if we, you know, if we could just much better define the junctions, right? So, kind of one of the best case scenarios for this is in this paper from IBM, where they use a laser to dial in the junction resistance, and they get about an order of magnitude improvement in junction specificity. And the exciting thing that I wanted to share, this is recent work from Rigetti, is they had this kind of discovery in the past year that, you know, you don't have to resort to these laser-based, very sophisticated systems that IBM is using. You can actually just put a probe station on your junction, on your qubit, and move current back and forth through the junction. And it's like a volt at about a hertz. It's a very simple setup. And it allows you, if you just apply a little bit of heat, it allows you to dial in the junction resistance extremely accurately, just as accurately as with this kind of $100,000 setup that IBM arranged. And I think this, you know, this is going to be really enabling for the field. As you can see here, it allows you to dial in your junction resistance as much more narrowly. This is like the initial junction resistance distribution. And then essentially after maybe an hour of aging, the distribution is this teal color. And so you have at least an order of magnitude improvement in the specificity of your junctions. Another cool thing about this is it's a new window into the chemical environment of the Josephson junction. These have been kind of opaque structures for a long. Yeah.
So you could do the previous slide.
Yeah.
The previous slide. Another question on this graph is that do they sort of take a measurement first of what each junction is initially, and then according because I assume that the duration of their current annealing has a direct result on the resistance. So each of the junctions get like special, like have a dedicated time. Sort of like,
So,
for example, if a junction that's a very low resistance, but you know, for longer than if the junction that has, or the all junctions get equal treatment.
no, so each is individually measured and tuned for like, you know, minutes. So what the blue distribution is here is if you just take the endpoint of that tuning process for each of those junctions and make a distribution. Then they went back and remeasured. This is like, you know, it's over the course of an hour or two, probably.
So just like each junction, the blue one is on each junction is tuning individually.
Yeah.
Okay.
So that's after it's making a histogram of the endpoint of tuning each junction. And then the light blue here is when they went back maybe an hour later, the junctions just drifted somewhat, they aged somewhat because they're in an ambient environment.
I have a couple of questions online too.
Yeah.
So basically one question about the GUI. Is it like making shadow masks or photo mask for application alternative to manual K layout?
Yeah, I mean, So sometimes, I mean, I use K-layout all the time. Sometimes you have to, but when we kind of have when we're kind of organized, we write Python scripts to make GDS files, and many people in the field have just spent months writing really annoying scripts to create GDS files, right? I think these AI tools are very powerful at automating that sort of thing and converting concepts about geometry into scripting to create geometry. So useful both for junction layout and circuit layout broadly.
For the etching, how selective is this etching? Is it like Bosch etch?
Oh, Bosch. I mean, so this is an argon ion mill etch, so it's not a Bosch etch is like a silicon etch. So yeah, if we look at the ABBA process as a function of temperature, we can see actually, you know, now the oxygen ions, you know, being pushed through the junction, and it's a new knob on the junction chemistry that we haven't had before. It's also an indicator of junction chemistry. So if you look at this ABBA effect in aged versus non-aged junction, there's a really dramatic difference. So it's actually telling you, but there's a long history of like, you know, the impact of annealing generally will tell you a lot about junction chemistry, but this is kind of a transport-based indicator of junction chemistry. It likely behaves very differently depending on impurities in the junction. And so why does this matter for the design problem that we're here to study? It's our view that this is going to enable a very different set of circuits than are currently used in superconducting qubits, because you get an order of magnitude better frequency definition of the qubits. We hope that we can do still better than that, because we're at will with voltage generator, programming in the frequencies very accurately, as you saw. If we can solve that kind of drift problem, perhaps we can really go beyond this tenfold improvement by more orders of magnitude. But if you do want to do this, and I'd say, probably everyone in the field is going to end up doing this quite soon, because it's just something you can do in any lab. It doesn't take any infrastructure, really. You do have to design your qubits so that you can make galvanic contact. This is not always the case with like XMONs. You want to be able to make galvanic contacts to regions with no high electric fields. And then you have to go, this means that you have to kind of go into each qubit and tune it, as we said. And so maybe that's not a scalable process, but I'd argue that using modern probing methods like this probe card, you could actually tune millions of qubits if you want to. Okay, so that's kind of it for my discussion of junctions and where that I'd like to help inform the design of qubits with junctions. I wanted to just kind of add this note regarding the design problem that, we of course want to be very accurate with microwave simulations and stuff, but you can kind of take the old-fashioned way and do analysis to design a qubit. So there exists a analytic solution.
Before we move on,
Yeah.
Someone is a little lost in what a shadow mask is.
What's a shadow mask? That was like 10 slides ago.
Yeah, sorry. I didn't catch this question until now.
So the shadow mask, So the way we're doing these shadowing processes is that you have two layers of resist, and the top layer is where your primary mask geometry is, and then the lower layer is just kind of suspending that mask, just holding it in place. So you have to have like a suspended geometry to create these projections of the physical vapor deposition process. And yeah, shadow, it's something that's been used for a long time with any number of materials. So it's a very useful process for kind of in situ making heterostructures between superconductors. So yeah, so say you wanted to just back of the envelope design a qubit. There exist closed form solutions for the capacitance of two coplanar rectangles. And one of my colleagues has even developed a simpler formula shown here that's a very good approximation to the complete analytical solution. And there exist further analytic solutions for the couplings of CPWs. In our experience, this has been really useful for just kind of simple design calculations when you don't want to resort to HFSS or any modeling software. It is once you have the capacitance of this object and you have the junction resistance, you can calculate just the frequency of that qubit, right? So that's about you're kind of halfway to a qubit design. And then, so the next step of constructing a qubit is that you have to make this kind of large scale superconducting base layer that defines most of your circuitry, in addition to the Josephson junction. And loss in that plays a big role in the lifetimes of the qubits that you observe. At least the maximum lifetime and kind of optimally designed qubits. For a long time, niobium has been used. In part, this is because it has a high, it has a critical superconducting temperature well above the boiling point of helium. Tantalum has been known for a long time to be and potentially much cleaner, but it doesn't form a surface oxide that's as ill-behaved as niobium. But it has a critical temperature very close to liquid helium, and this actually makes it quite annoying to work with to make circuits from, because for a long time people like to test their devices in liquid helium. So there's been a lot of work, perhaps in recent years, using tantalum for superconducting circuits and making very good kind of test qubits to look for materials, the materials limited loss rates in superconducting qubits. And so tantalum seems to be a very effective way to make considerably better superconducting qubits. One problem with tantalum is that if you deposit it at room temperature, you get a beta phase, so it's a different crystalline phase, with the phase shown here. That's very disordered, where you don't have this phenomenon with niobium. You can deposit it and make a good superconductor even at room temperature. So one way of getting around this is to grow a heterostructure between a thin layer of niobium and tantalum. And this is actually a very special material system So there's a quote from Ted Gabal in 1987 saying that niobium tantalum is essentially the closest realization of a perfect metallic superlattice because there's a very close lattice match between the niobium and tantalum crystal structure. So when we can actually see like an epitaxial relation between the substrate, if it's, you know, in the case of sapphire substrate, and the tantalum, because there's a perfect kind of interface between niobium and tantalum. And so it's actually quite unique system, but we like it because it allows us to grow tantalum at room temperature and have it still superconducting. So without getting too much into the characterization of this, one neat thing that we found was that just by kind of looking at this surface structure of these tantalum films, you can deduce the crystal structure and therefore see whether or not it's going to be superconducting at all. So this is, you know, the starting point is that you want to make sure your superconducting circuit is superconducting. And so if you look at one of these films, you end up seeing if it is alpha phase tantalum, you see crystallites that are kind of long, whether it's on silicon or sapphire. And so, you know, if you check out our work, you can actually just, in a fabricated qubit circuit, if you wanted to know the crystal structure, you don't have to do XRD or anything. You can just put it under the SEM and look at the crystallites. Another fun trick is that this room temperature process allows us to make air bridges completely of tantalum. We've heard about how that's used in circuits. And then another unique aspect of the tantalum sapphire system is that if we do go to high temperatures, and this is what we normally do for the base superconductor layer of our circuits, if you do go to high temperatures, you get a lattice matching between tantalum and the 111 orientation and the C plane of sapphire to within about 1.5%. And these films are far more ordered than any of the films that I described previously. So you get a very, very high quality film. So one metric for that is the resistivity ratio. Generally in superconductor or in metals, the ratio between the room temperature resistance and the low temperature resistance tells you about the crystalline quality. And yeah, so I mean, it was very dramatic when we started seeing films with this 111 orientation. It kind of like just snaps into place. You see this in X-ray diffraction, where suddenly the 110 reflections just disappear, and you get a 111 reflection that's far sharper than the reflections in the 110. And there's again, you can just like look at these films, and based on the appearance in SEM, you can identify them once you kind of have some idea. So in the 111 films, you really have to struggle to look for surface morphology. That's why this image is so crummy. But the surface morphology is just kind of a bunch of dark spots which correspond to point defects in the film. But it's a far kind of smoother film. And one way to quantify that smoothness is using synchrotron XRR. So this is at SLAC, we performed this measurement of X-ray reflection. And based on modeling this data, we can actually see that the 111 tantalum films are as smooth as the sapphire surface that we're starting from. So these are incredibly flat, way flatter than, for instance, the Josephson junction films that we were talking about. And so ideally, you actually make your Josephson junction out of something, this flat, this uniform. But we think they're also very good systems for just constructing the large structures of the superconducting circuit. And we can demonstrate that by doing loss measurements, and we get very high quality factors of resonators. So again, what does this all mean for circuit design? So there's been parallel work at Princeton, and one thing that they've seen is that in very clean tantalum films, you actually get this problem where you have very mobile vortices. And so you have to be somewhat more careful about including vortex traps, so the perforations that we all see in these circuit designs, in order to prevent those very mobile vortices from actually hurting your qubits. And generally, as you know from some of the recent work from Princeton, again, one can expect really high quality factors from similar tantalum films. Especially if you make your features very large, this is always kind of the case. We can also grow tantalum on silicon. Of course, this is viewed as a more scalable approach to circuit construction. In this case, the crystal structure of the tantalum films is far more complex, but based on others' results, we'd anticipate these films also allowing us to make really good qubits. So you get this quite crazy grain structure where you have kind of long grains and regions of flat grains. Because there's no crystallographic alignment between the tantalum and the silicon film.
There's a question about the phases of these films. Like, are they amorphous? Are they crystalline?
Yeah. So definition of crystalline varies, but with the tantalum on sapphire that I was just talking about that has very high Qs, it's basically crystalline. And in the it's basically a crystalline layer of tantalum on crystalline sapphire. With this would be polycrystalline. So you have crystallites that are on the scale of a micron. You can make essentially amorphous tantalum if you do grow tantalum at low temperature, you get this beta phase that I was referring to, and that's a amorphous phase essentially. The unit cell's like 20 atoms or something. So it's
For the niobium tantalum interface, do you need a niobium to be crystalline?
I'm sure if you worked at it, you could make amorphous niobium, but it likes to be kind of crystalline, like it likes to have this BCC structure. So it does have to be somewhat crystalline. Just to show kind of the difference between tantalum films on sapphire versus silicon. On sapphire, it's a very stable surface. This is why materials people like it. So even at quite high temperatures, you have no reaction with the tantalum that you're depositing. And the sapphire, if you grow on silicon, you get this kind of intermixing layer. It's probably doesn't matter very much for superconducting circuits at present, based on a bunch of groups' results. But it's not clear whether that's going to be limiting for qubit performance, at some point. And we've shown that we can make quite good qubits. So this is this region here is the tantalum. It's totally not clear, I'm sorry, but this is looking at the junctions, and this region is tantalum, and this is the Josephson junction, and the chip with 6 different qubits, some of which have ground plane perforation, some of which have been treated with this ABAA process. In this particular example, we didn't really see a distinct effect from either of these, and this is kind of a general problem with material explorations of superconducting qubits, is that we often don't have the statistics to make inferences about materials effects, because there are variations like this bit of gunk that's on this qubit number 1. And that's a problem that we're working on at Lawrence Livermore National Lab. As you can see, our best qubit has a T1 time of like 400 microseconds, which we're quite pleased at, and we hope I'm kind of advertising this because we hope that you can send your designs for us to make, and we can make you nice qubits using this process. And so this, that's the average T1 time measured over like a day for those who care. And we've also, people have been talking at this conference about these published designs, right? It would be really nice if we all had kind of a common database of designs to compare, but people are naturally protective of their designs, I would say. But in one kind of rare case, the VTT team published, their GDS files, from which they had made qubits with very good coherence times. And this is, published in the past year. So we went in and made qubits using this same design file, substituting in our junctions. And I would say for reasons we don't totally understand, we have about a 30% lower T1 time, but still, quite comparable. And we were pleased with that just because, it's not our design, and it was just, one-off fabrication and measurement. And if you look at the distribution of T1 times we're measuring, it's considerably narrower, and perhaps that's related to our kind of much chunkier junction design compared to this VTT Manhattan style junction design, which is quite kind of spindly. The fact that I'm using this chunky and spindly, I mean, I wish we had like really nice microwave models to understand, how these design choices really impact circuits. It doesn't exist.
So your theory is that there's different surface participation ratio between like when you read the junction like this.
There's different, I mean, there's kind of different distributions of TLS in a sense. I mean, it's a different ways of looking at it, but there are instabilities in all these aluminum surfaces. And so if you, I think that, having these really narrow features, you have kind of more, and somehow that it's somewhat more unstable, at least to fluctuations at some time scale. I think that's so that's kind of so I as I say, if we've developed this all tantalum fabrication process, if people have designs for multi-qubit circuits using the design tools that we've been learning about at this conference, I'd be really just reach out, and we'll try to harmonize the designs with our process. It's always kind of a challenge to do so, and we're not quite Lincoln Labs that we can we have the like perfectly defined set of design rules we can just hand you. But if you have developed designs, we're happy to work with you. Also, you know, I think AI is extremely powerful for circuit design, and it will change the way we do circuit design, not just in the quantum world, but broadly. And yeah, I think if you're a graduating grad student, we have a potential postdoc position in the next year or so. So feel free to reach out to me about that.
Yeah, the answer to this. You know why that like gunk
Mhm.
on that qubit one that you were showing?
Yeah.
It reduced the T1 time, but it also like narrowed the distribution of T1 time. It's too many guesses for one.
Yeah, that's what it looks like. Oh, yeah, no, I don't really know. Yeah, I don't know. Sorry.
What does native oxide do when it goes on the qubit?
What does native oxide
Yeah,
do?
that's a question.
So the native oxide has, in no case that I know, a crystallographic relationship with the metal that it's growing on. So it's amorphous, it's kind of structureless, and it's under-coordinated in some way. So they're always, when you go to low temperatures, there are always kind of degrees of freedom within that oxide. And that's, you know, what we treat theoretically in the TLS formalism, right? And is that?
So, you mentioned that you're guys are using argon ion melting.
Yeah.
In the process of removing native oxide. So, I've also noticed that from my research that iron melting can actually harm the substrate. Sapphire substrate creates a layer of amorphous sapphire-ish thing that reduce your overall coherence. So how do you guys approach this problem?
Yeah, well, so that's what I was kind of talking about with this, I guess, totally ambiguous plot here, which is that you use the shadowing. So the argon milling is a directional process. So if you tilt your substrate and do the argon milling, your argon ions aren't hitting the kind of high aspect ratio features of your pattern, of your mask. So you can avoid amorphizing the surface near your qubit, where your qubits are, just by careful consideration of the angles when you're doing this.
What is the angle?
It's like, you know, 45 degrees. Keep it simple. So yeah, we're talking about pretty significant tilts. And you know, there are various approaches to make your circuits less prone, like susceptible to errors in that tilt, that clever people have come up with over the years.
There's no more questions, everyone. Let's thank our speaker.